Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Welcome everyone. We're very happy to have Lirong Xia from Duke who will tell us about computational social choice.
Okay, thanks Yura for the introduction, and thanks very much for inviting me for the interview, and thanks again everybody for coming. So in the next hour, I'll be talking about my PhD work at Duke, which is computational social choice. I've been mainly working on the algorithmic, strategic, and combinatorial aspects of computational social choice. And as you know, I'm Lirong Xia. I'm a PhD candidate at Duke University, working with Vincent Conniser. So I'm going to start with a very brief and general introduction to computational social choice, because you probably haven't heard of this term. What is computational social choice? What the hell it is? So it's a very new, newly born, interdisciplinary area. And then I'm going to talk about a specific paper of mine, the study of a voting game called the stackable voting game. Okay, so most of my work was about voting. Voting, as you know, is a way for the voters to represent and aggregate their preferences over a set of candidates or a set of alternatives. So for example, here we have three alternatives or three candidates. We have Obama, Clinton, and McCain. And we have three voters here. Each voter uses a linear order over the set of alternatives to represent his or her preferences. Okay? And then they submit the vote to a center, and the center is going to use a voting rule to select a single winner based on these reported preferences. Okay? So for example, here we use a voting rule called the plurality rule, which has been used in United States presidential election for many years. And the plurality rule selects the alternative that is ranked in the top position for most times. For example, here Obama is ranked in the top position for 2 times, and McCain is ranked in the top position for 1 time, so Obama is the winner in this case. Right. So computational social choice, it concerns computational issues in preferences and information, representation and the aggregation, especially in the setting of voting. Right? Because you know social choice is a very big area containing voting and fair division and judgment aggregation and so on. But so far, voting is still the mainstream of social choice. And it is a newly born area sitting in the intersection of artificial intelligence, because that's where we publish most of our papers, and of course theoretical computer science, because so far most of the results are theoretical results, and we use a lot of the concept, tools, methodologies, whatever else in theoretical computer science to help social choice. And of course, you know, social choice is a well-developed area under economics and political science. Okay, and it seems to have been attracting a lot of attention, especially in recent years. Let me show you some data. In each Chi 09, there were 3 independent sessions on computational social choice, and in ALMAS last year and EC last year, there were 1 independent sessions respectively, and especially in IIII last year, there were 6 independent sessions on computational social choice. And there is a closely related conference called Algorithmic Decision Theory, and there is a workshop called Computational Social Choice Workshop, which was held every other year since 2006. Okay, so this seems to be a hot area, but of course you may ask why people care about computational social choice, right? So first question to ask is why people care about social choice. I think the answer is pretty much very obvious, right? Because in many real-life situations, people or intelligent agents, they have conflicting preferences over the set of alternatives, but they have to make a joint decision. For example, in United States presidential elections, everyone has different preferences over the candidate, but you can just select one winner. You cannot select 1,000 presidents. That's definitely not going to work. And sometimes you want to give a full ranking over those universities for the student to apply to them. And on the other hand, you want some of the universities want to rank all of those applicants just to give them offers. Right? And the computational social choice has huge application in internet economy, like sometimes you want to aggregate the user's experience about some movies, some product, or some opinions, and so on. Okay? So, and why computational social choice is important? I think to understand this, let's look at the interplay between computer science and social choice. Okay? So from computer science to social choice, computer science basically provides a computational way of thinking about many traditional problems in social choice, like how can we compute the winner more efficiently, how can we use computational complexity as a barrier against strategic behavior, and so on. And from social choice to computer science, there are many well-developed methods of aggregating the voters' preferences, like many good voting rules, plurality, veto, border, whatever else. And those could be used for in computer science, especially in multi-agent systems. So, and computational social choice is closely related to some other interdisciplinary area. I know some of you are working on this. For example, it's closely related to algorithmic game theory, because in both computational social choice and algorithmic game theory, one of the core problems is how to analyze and prevent the strategic behaviors of voters and the strategic behaviors of players. And it's also closely related to algorithmic mechanism design, because voting is a special mechanism without money. And in algorithmic mechanism design, researchers care about designing mechanism with money. So this seemingly very small difference actually led to very different tastes of research, very different results, and so on. Okay? So I hope you are convinced why computational social choice is important, but why it is challenging, why we need to work on that. I think the hardness mainly comes from two facts. The first fact is that the problem of aggregating the voters' preferences are sometimes extremely hard, especially when we have a big number of alternatives, like we have a very big pool of candidates, right? And another aspect is the methodologies are very hard to develop, because now the voters' preferences are represented by ordinal linear orders. It's ordinal. It's not cardinal like in algorithmic game theory or algorithmic mechanism design. So it's really hard to convert these preferences representation and aggregation problem into some optimization problems. It probably don't work. Okay, so this is a very general my research spectrum, and I've done some work on economic side of computational social choice, which mainly care about the combinatorial voting, where we have extremely large number of candidates, and the set of candidates has a combinatorial structure. But I'm not going to talk about this. Many talk about this in this talk. I'll be focusing on the computer science aspect, and well, I've been working on the algorithmic aspects of preferences, representation, and aggregation. And in both of these research directions, strategic analysis plays a very important role. So I'll be talking about one of my work on analyzing and computing a very special game, voting game called the stackable voting games. Okay. So before we go into the technical section, any general question about computational social choice? Okay, that's good. So before talking about the stackable voting games, let me just go over some basic concept of game theory. I know pretty much, maybe almost all of you know what is game theory, what is Nash equilibrium, what is subgame perfect Nash equilibrium, but it's just to make sure that everyone is on the same page. Okay, so game theory is a useful way or popular way to model real-life strategic situations. So usually it can be modeled as a normal form game, where we have set of players. For example, here we have two players, the row player, who is the red prisoner, and the column player, who is a blue prisoner, right? And then they're going to choose their moves from a set of strategies simultaneously. For example, they can choose either to cooperate or to defect. And as soon as they have chosen a strategy profile, there's going to be an outcome associated with this strategy profile. And both of these players, they have preferences over the outcomes. The preferences could be a cardinal represented by the utilities, or it could be ordinal, like both of them prefer win much to win, to lose much. And one of the most important solution concepts in normal form games is Nash equilibrium. So here we only focus on pure Nash equilibrium, which is a strategy profile where no player can benefit from deviating from his current strategy. Right? So for example, in this game, the only Nash equilibrium is both of them choose to defect, because the red player cannot benefit from moving to cooperate, and similarly for the column player. Right? So this is a simultaneous move game, but sometimes you want to study a situation where those players that just choose their moves in turns. So that is captured by a concept called extensive form games. right? For example, in the previous example, if the column player, the blue player, want to move first and then followed by a red player, then this is an extensive form game. Again, we have set of players, and the game is represented by a tree. Here, each node in the tree represents the move of one of the players, and all of the outgoing edges represent the set of available strategies, right? And the terminal states are associated with outcomes. And these players have preferences, either cardinal preferences or ordinal preferences over these outcomes. Okay. And for extensive form games, one of the solution concept is called subgame perfect Nash equilibrium. It is a refinement of the Nash equilibrium. So it is defined to be a Nash equilibrium. Well, if you restrict this Nash equilibrium to every subgame, it is still Nash equilibrium. So, for example, in this game, there is one unique subgame perfect Nash equilibrium, which can be computed by a backward induction. So if you look at this state, it is the red player's turn, and you can see that he prefers win much to win, so he's definitely going to choose to defect in this state. And similarly, he's going to choose to defect in this state. And if you look up at this player's move, he actually prefers lose to lose much, so he's definitely going to choose to defect. This is the only pure subgame perfect Nash equilibrium in this game. So, yeah.
Sorry, what's a subgame?
Oh, subgame is, well, in this case, it's represented by a subtree. So, right, so it's a subtree starting from here, right? So if you think about this strategy profile, if you restrict your attention on this subtree, then it basically says he's going to choose to defect, and this is a Nash equilibrium because we only have one player. Right? He's going to do his best. He prefers lose to lose much, so he's going to choose to defect. And the formal definition of subgame is a little bit more complicated, but in this case, it just means.
Can you tell us the formal definition then?
Oh, okay, sure. Well, so then it involves talking about the information sets. And so information sets basically are kind of relationships among those nodes. So you have two nodes in the same information set, basically means that you cannot distinguish from these two states. Right? So if you draw an information set here, then it basically means that you cannot distinguish either. You can be either at here or at here. You cannot tell. Then a subgame, there are multiple definitions for subgame, but the simplest one is that you require the root must be the only one state in his information set. Okay, so I know it's a little bit complicated, but actually in this talk, we're not going to talk about the information set, so just forget about this definition. Just think about this tree, subtrees.
Can you just tell us a definition that's enough for what you're going to talk about in this talk?
Yeah, sure. I will.
Okay.
I will do it soon.
Thanks.
So how it is related to voting games? Of course, let's first look at the usual process of voting. This is a very common process of voting. Suppose we have two voters, right? We have Superman, Mr. Superman, and Mr. Iron Man. And we have a set of 5 alternatives, right? We have Obama, Clinton, McCain, and 2 poor other guys. And these two voters have ordinal preferences over this set of alternatives, and we're going to use the plurality rule to select the winner. Right? And plurality rule, if you still remember, is the voting rule that selects the candidate that is ranked in the top position for most times. And in terms of when we have a tie, then we're going to break tie using this tie-breaking mechanism, where Obama has highest priority over Clinton or McCain and over 2 poor other guys. Okay? So suppose this is the true preferences of the voters, and if they submit their true preferences, their votes, then you can see Clinton is going to be the winner. Because you have tie between Clinton and McCain, and if you look at this tie-breaking mechanism, Clinton has a higher priority over McCain. Okay? So Clinton should be the winner if both of them submit their true preferences. But how to model this situation as a game? There's a very natural way to do that. We have n voters. Suppose we have n voters. In that example, we have 2 voters. Now, each of these voters can be thought of as a player. And the set of strategies are exactly the set of votes they can report, which is the set of all linear orders over the set of alternatives. Right. And the preferences of them is, again, the set of all linear orders over the alternatives. Okay. And each strategy profile is going to be associated with an outcome, which is the winner, under this voting rule R. So this is how to model the voting situation as a simultaneous move voting game. So any question about it? That's great. So what's the problem with this? Of course, you can model it as a normal form game, and then you can ask what are the Nash equilibria. So the problem is that usually, if you model the game like in this way, then we have too many Nash equilibria. And many of them doesn't make much sense. They're very bizarre ones. For example, suppose we have two alternatives, A and B, and we use the plurality rule to select the winner. In this case, plurality rule is called majority rule. And suppose that everyone actually prefer A to B. Okay? If you look at a profile where everybody actually voted for B prefer to A, then this is a Nash equilibrium, because no single voter can change the outcome by voting differently. Suppose we have 3 or more voters. So you can see this doesn't make much sense, right? So of course you may say, okay, now everyone has a dominant strategy, which is A prefer to B. How about we just look at the refinement? Well, you ask every voter to submit their weakly dominant strategy, and that could solve the problem. That's true, but only for 2 alternatives. As soon as we have 3 or more alternatives, nobody has dominant strategy, and now you always have the similar situations. So that means in the simultaneous movie games, you're going to have a very big equilibrium selection problem. So this is a big problem. And so the way we want to get around this problem is that we ask ourselves, does there exist any real-life voting settings such that we don't have this equilibrium selection problem? We have unique outcome. Then we can start to work on it. How can we compute it, and how can we analyze it, and do stuff like that? And it turned out that there exists such kind of situation. Well, is exactly the situation where voters come, they don't vote simultaneously. They come one after another, cast a vote, and leave. And all of the later voters can observe the votes of all previous voters. Right. So there are many real-life situations like this. For example, if I want to buy a presenter for the interview, what I can do is that I can go to bing.com and look for this product, and then I found it on Amazon. So now what I can see the price of this product, I can see how much I saved, and I can also see the star level of this product. It's a 4-star product. So how do we come up with this 4-star? It's calculated by the votes of the previous users. So let's look at the history. The first user tried this item, and he really liked it. And he thought this is a very brilliant item, so he voted for 5-star, right? He cast the vote and leave. Now the second voter came, and he can see the vote of the first voter, which is 5-star. Maybe he really thought this product was 4-star. But then just to balance the first voter's vote, he cast 3-star for this item, right? So he cast the vote and leave, and then here comes the third voter, and so on. So this is just an example of this voting setting in internet economy. But actually in many real-life situations, for example, in presidential election, if you're going to vote today, essentially you can see the votes of all previous voters because they are broadcasted. You know how many voters voted for Obama, how many voters voted for McCain, and so on. Right? So this is our setting. We model this voting setting as an extensive form game. So this is the related question, how our voting game is an extensive form game. So we assume that voters vote sequentially and strategically, one after another. We assume, without loss of generality, that voter 1 voted first, cast his vote and leave, then followed by voter 2, and so on, until voter n. Right? So this is an extensive form game where each stage corresponds to the move of one voter. Like in stage I, it is voter I's turn to cast a vote, and the states within this stage I is composed of all possible combination of votes of the previous voters. So this is actually the history. He can observe its set of a possible world he could be in. And any terminal state is associated with a single winner, the winning alternative under some voting rule R, which was given exogenously before this process. So we have some assumption about the knowledge and information. We assume that at any stage, any voter knows the order of the voters. They know that voter 1 voted first, followed by voter 2, voter 3, and so on. And they can see the votes of the previous voters. And they also know the true preferences of the later voters. This is just a standard completed information setting, but of course you may say this is not very natural. How about let's just think about Bayesian setting, right? That's true, but actually because one of our main results, theoretical results, is a paradox for this voting game. So the paradox is naturally carried over to Bayesian setting. So just for this work, let's forget about Bayesian setting, just focus on completed information setting, okay? And they also know the voting rule R that is going to be used to, in the end, to select the winner. For example, they know the voting rule is the plurality. Okay, so this is setting of the game. And we call this a stackable voting game. And as I mentioned a couple of slides ago, one of the most natural solution concept in stackable voting game is subgame perfect Nash equilibrium. But of course, here there could be many subgame perfect Nash equilibria, but it is not very hard to show that the winner in all of these subgame perfect Nash equilibria are the same. So we let SGRP denote this winner. SG means stackable game. R is the voting rule we use in the end to select the winner. And P is the true preferences of voters. Okay. So any question about this setting? I'm going to show you the example next page, but just make sure that everybody, yeah?
Can you control your position in the order?
No. Let's say in this work, we just think about a fixed order. So an example of showing how can we compute that winner in the subgame perfect Nash equilibria is suppose we have two voters again, Mr. Superman and Iron Man, and they have preferences over the set of 5 candidates, and they're going to use the plurality rule to select the winner in the end. So remember that plurality rule is a voting rule that selects the candidate that is ranked in the top position for most times. Okay? So, and then in terms of tie, we're going to use this tie-breaking mechanism. So this is a game tree of the stackable voting game. We assume that Superman voted first, followed by Iron Man. This is the first stage, the stage for Superman, and the second stage is for Iron Man. We have a couple of stages. Okay? And every terminal state is associated with a winner. For example, this terminal state says that Mr. Superman had voted for McCain, and Mr. Iron Man voted for Clinton. So based on this tie-breaking mechanism and voting rule, Clinton should be the winner, right? So now we want to compute the winner in the subgame perfect Nash equilibria by backward induction. And the idea behind backward induction is that we're going to compute at any state who is going to be the winner if we reach that state. So we're going to do it in a bottom-up flavor, right? So the first step is that we are going to look at the leftmost state, and it's Mr. Iron Man's move. You can see that actually Clinton is his most preferred candidate. So he's definitely going to vote for Clinton to make Clinton win. Now, what we do, what we know is that we know if we reach this stage, then Clinton should be the winner. Similarly, if Mr. Superman voted for Nader, Clinton should be the winner. Mr. Superman voted for Parr, Clinton should be winner. If the Mr. Superman voted for Clinton, then Clinton is definitely going to be the winner. But things only changes when Superman voted for Obama. Here, at this stage, whatever the vote of the Iron Man is, the winner is always going to be Obama. Right? So we know that if you read at the rightmost state, winner is going to be Obama. Now it is Superman's turn to choose the winner, choose his move to select the winner. And here's actually comparing between Clinton, and Obama. So even though he doesn't really like both of them, he still prefers Obama to Clinton. So he's definitely going to vote in this way to Obama to make Obama win. So this is how do we compute the backward induction winner. And remember that Obama is the winner. We're going to come back to this fact later. Okay. So any question about backward induction in this voting process?
Can you explain why Obama won?
Thanks. Okay, so just some literature about this voting game. We're not the first to look at this kind of situation where voters come one after another and the later voters know the previous voters' vote. There are a couple of papers before us, but our setting and the results are very much different from theirs. And in some of these papers, the set of alternatives are restricted to be 2 alternatives, like I think in these 3 papers. In the last paper, they only focus on the plurality rule. Here in our paper, we don't limit the number of alternatives. We don't number the voting rule used. We're going to show general results, and actually 2 general results for this very general setting of stackable voting games. And one of our main results, main theoretical results, was the paradoxes, which were kind of a price of anarchy result. And price of anarchy is a useful concept which captures the cost of the strategic behavior in games. And because in our setting, we don't have cardinal preferences, so our paradox can be seen as an ordinal version of price of anarchy result. So this is just a very high-level description of our result. I'm going to show you what our paradoxes are. But before that, I think it's very natural to ask the following two questions related to the stackable voting games. Right. The first key question is that how can we compute the backward induction winner more efficiently, more computationally efficiently, for general voting rules? It's not only for plurality, not only for veto or border or whatever else. Okay. So the second key question is that now we only have one, we don't have any equilibrium selection problem, so we have only one winner. Now we can ask ourselves how good or how bad is this backward induction winner. Okay. So I'm going to focus on the first on the first issue, how can we compute the backward induction winner? And the key idea behind our computation technique is to explore the equivalence relationship among these profiles. For example, let's just look at the plurality rule. Well, we have 160 voters who have already casted their vote, and we have 20 voters remaining. Right? So the first profile is composed of these votes. We have 50 voters voted for X preferred Y preferred to Z, 30 voters X preferred to Z preferred to Y, 70 voters Y preferred to X preferred to Z, and 10 voters Z preferred to X preferred to Y. Now, this profile can be uniquely characterized by a vector of 3 natural numbers. Right? Because for plurality rule, we only need to know the number of times where each alternative is ranking in the top position. Right? So here, this profile can be captured by 80, which is the number of times X is ranked in the top position, 70 for Y, and 10 for Z. Now I'm telling you, this profile is essentially equivalent to another profile where X is ranked in the top position for 70 times, Y for 60 times, and Z for 30 times. Why? Because remember that we only have 20 voters remaining. So whatever the votes of these 20 voters are, they're never going to make Z win. Because the cost difference between Z and X and Z and Y, they're too large, larger than 20. And another thing to note is that the score difference between X and Y are the same in these two profiles. So that means whatever the votes of these 20 voters are, the winner under these two profiles plus these 20 voters' votes are always going to be the same. So in that sense, these two profiles are equivalent. Okay? And this is our general technique to, And this equivalence was, forget about the reference, it's captured in a concept called the compilation complexity, which was introduced by Chevrolet or in Ichkai 09, and then we have some work in another paper in III-10, just exploring this kind of equivalence relationship for different voting rules. This is only for plurality. Plurality is very simple, but for other voting rules, it's not quite clear how can we build this kind of relationships. And these kind of relationships can be very useful in our computation of computing backward induction winner, right? Because there's no way you can avoid the backward induction step. You must be able to know at each state who is going to be the winner in order to compute the backward induction winner. So now, how can we save some time? We can look at the voting rule R. We first explore these equivalence relationships among the states, among the profiles, meaning that is the states, and then we can merge many of these states to an equivalent class. So when we do the backward induction step, for each equivalent class, we only need to compute the winner once. So this can actually drastically speed up the computation, and which will be very useful in our later simulation. You're going to see the simulation results. Okay. So now let me talk about the main theoretical results, which answers the question how good or how bad the backward induction winner is. So I'm going to show you a paradox of voting in the stackable voting games. If you still remember a couple of slides ago, I showed you a voting game where we have two voters, Mr. Superman and Mr. Iron Man. And if Mr. Superman voted first, followed by Iron Man, and they use the plurality rule with a specific tie-breaking mechanism, then hopefully you still remember Obama wins. Right? So what's wrong with it? The problem is that Obama is ranked in the bottom 2 positions in these 2 voters' true preferences. So to make things worse, both of them prefer Paul to Obama, prefer Nader to Obama, prefer McCain to Obama, and even Clinton is arguably better than Obama because at least Clinton is ranking in the top position for one time. So that seems to say that we have selected the worst outcome, the worst candidate, right? So how this happened? Of course, you can ask the question, is it because of the bad nature of the plurality rule, or is it because we try to construct the tie-breaking mechanism very carefully, just to come up with make everybody nasty, or it is because of the strategic behavior? Our answer is, it is because of the strategic behavior, by showing a very general paradox that works for almost every commonly used voting rule. No matter what is the voting rule used, you're always going to end up with a very nasty situation. That's what we want to show. So to present our theorem, let me first introduce a concept called domination index. The domination index is defined for a voting rule R with respect to a number of voters n. Right? Please remember that the domination index is defined for a voting rule. It is not defined for the stackable voting game using this voting rule. Okay? And it is denoted by DIRN. DI means domination index. R is the voting rule we used in the end, and n is the number of voters. Okay? And it is the smallest number k such that for any alternative C, any collision of n over 2 plus k voters can guarantee this given alternative C to be the winner. So what do I mean by guarantee? I mean there exists a way for this n over 2 plus k players, voters to cast their vote such that no matter what the vote of the other voters are, this C, this given alternative C, is always going to be the winner. Okay.
So they know what the other voters do, or
they don't know. Whatever the other voters' votes are, there exists a way for them to collaboratively. For example, they all rank C in the top position, and whatever the other case.
But that sounds like the other way around. So you're saying a stronger thing than that there exists a way for them to vote such that whatever the other people do.
Yeah, exactly. Yeah, that's
so
what I
mean. Not just whatever the others do, there exists a way.
Right. Yeah, exactly as you said. There exists a way for them to cast a vote in collaboration such that whatever the other guys' votes are, C is always going to be the winner. Okay. Some very quick facts about domination index. First, the domination index for any majority consistent voting rule is 1, very small. So what is majority consistent voting rule? A voting rule R satisfies majority consistency if whenever the majority of voters rank some alternative C in their top positions, this alternative C is always going to be the winner, no matter what the other preferences and other votes are. So you may think this is a very natural condition because the majority of voters already agree that C should be the best one, so why don't we just select C? And actually it turns out to be it is a very natural condition. And actually any Condorcet consistent voting rule satisfies majority consistency. Condorcet consistent voting rule is already a very big class, including like Maximin, Copeland, like Kameny, and Rankin-Pales, and many others. And plurality with runoff, buckling, and STV, and some other voting rules, they all satisfy majority consistency. Yes?
I'm confused about STV being on the list, because STV is different. It's that you're electing multiple candidates.
STV selected just the one that is eliminated in the end. Right. So if the majority of voters already rank some candidate C in their top positions, this alternative C is never going to be eliminated in any round. So that means he is definitely going to left to the end. Right. So of course you can use STV to generate a full ranking of the alternatives, but of course the top ranked alternative in that output ranking is the winner.
Okay. So just guaranteeing that.
They can guarantee that C.
Okay.
Yeah. And of course, there is only one exception to this domination index to be 1, which is position scoring rules. And it's not hard to show that for any position scoring rules, the domination index could be as large as n over 2 minus n over n. This is much larger than 1. Okay? And please remember that the domination index is defined for voting rules with respect to the number of voters. It is not a property for the voting game using this voting rule. Okay? And it is closely related to a concept called anonymous veto function, which was defined by Moody in his famous book in 91, but I'm not going to talk about this stuff. So let me just show you the main theorem. Our main theorem says that for any voting rule R, any number of voters n, there always exists an amplifier that is composed of n voters such that, first, many voters are miserable, which says that the backward induction winner of the stackable voting game using this voting rule R is ranked somewhere in the bottom 2 positions in almost all voters' true preferences. Just with some exceptions, a number of exceptions is related to the domination index. So you can see that the number of exceptions is 2 times the domination index. Okay? So this is the first kind of paradox. And the second kind of paradox says that if the domination index is smaller than n over 4, then the backward induction winner loses to all but one alternative in their pairwise elections. So alternative A loses to another alternative B in pairwise election means that the majority of the voters prefer B to A. Okay? So, and this result doesn't depend on any tiebreaking mechanism, doesn't depend on any voting rule you use. As long as the domination index is small, you're going to end up with a very big problem. Okay? So, I think I will just show you a very brief idea behind the in the proof. So the proof is by construction. The profiler actually itself is very simple. But what's really hard is how can we show the winner? Right? This is not a trivial task. So to show the winner, we have proved a lemma, which is a sufficient condition for a given alternative D not to be the backward induction winner. Right? So we can show that for any profile P, an alternative D is not the backward induction winner if there exists another alternative C that kind of block D from winning. So I mean, by blocking D from winning, I mean there exists a subprofile P of these true preferences PK that satisfy the following 3 conditions. The first condition says that this subprofile should be large enough. That should be composed of more than n over 2 plus domination index voters. And second, in all of the votes in this subprofile, C should be ranked higher than D. And third condition is a little bit complicated. It says that any set of alternatives that have ranked higher than C, not than D, than C, in a later vote in this subprofile must be a subset of the set of alternatives that are ranked higher than C in an earlier vote in this subprofile. Okay? So if these 3 conditions are satisfied, then we can claim that D is not a winner. So this is how we show the paradox. So we constructed a profile like this. We have first n over 2 minus domination index votes whose true preferences are C3 prefer to C4 all the way down to Cm, prefer to C1, prefer to C2. And then we have 2 times domination index votes whose preferences are C1 prefer to C2 all the way down to Cm. And for the remaining n over 2 minus domination index votes, we have C2 prefer to C3 all the way down to Cm prefer to C1. Now I'm going to show you that C1 is the winner of the backward induction. C1 is the backward induction winner, right? And as soon as we show that C1 is the winner, then we have the paradox. So how can we do that? We're going to use the lemma. We first show that C2 cannot be the winner, and we use C1 to block C2 from winning, and the subprofile is a profile composed of the first part and the second part. Then, for any alternative of C3, C4 all the way down to Cm, we use C2 to block them from winning, right? And the subprofile is composed of the profile in the second part and the third part. And you can check it. I know it's probably a little bit hard to follow it here, but this is just show a very high-level idea of how can we show who is the winner. Okay? So the only remaining possibility is that C1 is the backward induction winner. So now this is the way we can see who is the winner, and this is paradoxes. These are the 2 paradoxes. Okay? So what does this paradox tell us? So this paradox basically says that, for any voting rule R that has a very low domination index, sometimes we're going to have a very bad situation where the backward induction winner is extremely undesirable for almost everyone. And please remember that the domination index for any majority consistent rule is 1. And majority consistent voting rule is a very big class of voting rule, which includes almost every commonly used voting rule, more than 10 of them. So that means we have a general paradox for almost every voting rule. Okay? But you may ask, okay, this is just the worst case result, right? So you just show there exists some situation where everybody is miserable, but what happens on average? We are not able to come up with any theoretical results because the main hardness is that it's extremely hard to say who is the winner, right? So that lemma is the best thing we obtain. So the backward induction winner is not that obvious. I mean, sometimes your intuition could be very wrong. So, but what we can do is that we were able to run some simulations and draw some conclusions. And that could be maybe useful in our further research. And what we could show is that by simulation, the number of voters who prefer the backward induction winner to the truthful winner is actually larger than the number of voters who prefer the truthful winner to the backward induction winner. So let me show you some simulation results. Our setting is like this. For any of the number of alternatives ranging from 3 to 7, and any number of voters ranging from 2 to 19, we draw 25,000 profiles uniformly at random. Okay? And then we test, we compute the backward induction winner by using the technique I showed you in the very beginning. And we have tried plurality rule and veto and the max min and some other voting rules. Here I only show you the result for the plurality rule, but the result for other voting rules are very similar. So I think the most important part is figure A, which shows the comparison between the backward induction winner and the truthful R winner. The x-axis is the number of voters, right? And the y-axis is the percentage of voters who prefer the backward induction winner to the truthful R winner minus the percentage of voters who prefer the truthful R winner to the backward induction winner. So this number is larger than 0, then it means that on average, more voters prefer the backward induction winner. So yeah.
So to compute the backward induction winner, you just have to explore the whole tree? So it's
kind of. But yeah, we can make it faster, much faster actually, by using those. We're figuring out if you still remember those relationships. Okay. And only by doing that, we can try like 19 number of voters. Otherwise, if you just use the brute force, then maybe you're going to end up like 10 or 10.
So it's still exponential, presumably?
Yeah. This is actually an open question. What is computational complexity of computing backward winner? So it's very natural to conjecture it's p-space hard, but we're not able to prove it. Okay. So, you can see that as the number of voters goes to infinity, there seems to be a limit for each number of alternatives, right? And these limits, they all seem to be larger than 0. So it kind of suggesting that the backward induction winner is more favorable, right? So this is our figure A. And in figure B, we show the percentage of profiles where the backward induction winner is exactly the same as the truthful R winner. So you can see that there seems to be a limit somewhere for each number of alternatives, and the limit seems to going down as the number of alternatives gets larger. Okay. So this is just some quick facts we can draw from the simulation results, but still we are looking for some theoretical proofs. And these results, they are not actually saying that the backward induction winner is better. It's absolutely better, but this is just some perspectives we can say about the backward induction winner versus the truthful R. Okay, I'm pretty sure you are a little bit tired, but just to sum up, I've mainly working on computational social choice, which is a rapidly growing new area in artificial intelligence and theoretical computer science and economics and political science. And I've been mainly working on 3 core problems. I've been working on algorithmic aspects and strategic analysis. Here in this talk, I covered a little bit the intersection of them, but I didn't talk about some other work on combinatorial voting. And if you still remember the research spectrum of mine, on the economic side, I've been mainly working on combinatorial voting, which is a voting setting where we have an exponentially large number of candidates, and these candidates have a combinatorial structure. And I've been mainly working on incentive analysis, which is we study another kind of sequential game where voters vote on issues sequentially. And I've been working on normative properties. We have tested whether some voting rules satisfy some desired properties like neutrality, Pareto efficiency, and so on. And I've been working on extensions and computational aspects of commutational voting. Okay. And on the computer science side, you already seen my work on how to analyze and how to compute the game theoretical solution for a type of separate voting games. But I also have done some work on preventing the voter's strategic behavior using computational complexity. Here, the idea is very much like in cryptography. And if you are keeping an eye on the communication of the ACM, recently there is a very nice survey on this line of research, how to use computational complexity to protect our elections. And that was chosen to be the cover story of recent communication of ACM. It's a nice survey, you can read it. And I've worked on preference elicitations. Here the problem is how can we elicit voters' preferences, those pairwise comparisons, to speed up our computation. And very high-level objective of my research is to help people or intelligent agents to represent and aggregate their preferences in a sounder and computationally more efficient way. Okay? So for future research, if you still remember this interplay between computer science and economics, especially social choice, from computer science to social choice, I plan to work on maybe using new ways to prevent voter strategic behavior. Because even though we can use computational complexity, recent research have been showing that this is not a very strong barrier. So we have to look for more ways, right? And I've been working on how to analyze voters' behavior and collisional formation in maybe social networks or in some other situations. And I'm looking for new and better tools for voting in combinatorial domains. And from social choice to computer science, basically we want to find new applications. Okay? So how can we use that voting rules to help robots or software agents to make joint decisions? And how can we vote in social networks and aggregate users' preferences over products or movies in electronic commerce? And another thing I'm extremely excited about is that we have developed new ways to help Duke Computer Science at graduate admission to rank those applicants. And we are trying to employ that approach, and we'll see how it goes. And beyond computation and social choice, I'm also broadly interested in some other topics in theoretical computer science and artificial intelligence and economics. For example, I'm interested in algorithmic game theory, algorithmic mechanism design, and the reasoning under uncertainty, machine learning, social networks, and especially prediction market. We've been working on it. So I'm ready to take questions. Thank you very much. Yeah.
I guess something I'm still grappling with is how to evaluate any of the choices, because we still don't have a good way of turning profile into a winner in general. And sort of how do you evaluate the quality of the game when you don't have sort of a clear rule to follow?
Well, that's a good question. So so in terms of game, I don't know the answer yet, but for voting rules, in terms of social choice, I can tell you the answer. So economics have been, people in economics have been working on basically two approaches to evaluate whether a voting rule is good or not. So one approach is called the axiomatic approach. Probably you know the errors and possibility theorem. So because we don't have a numerical value, we cannot basically convert those ordinal preferences or aggregation problems into a numerical value and say, oh, okay, so we have higher social welfare, so this voting rule is good. But you can design some properties that are kind of desirable, like anonymity or IIA or unanimity. Those are in the errors and possibility theorem. But of course, there are others, like Pareto efficiency and some others. This is one line of research. How can we evaluate a voting rule? But most of the research over there are negative. You have too many, actually way too many impossibility theorems. And another way, maybe more constructive way, is let's say it's a maximum likelihood approach. So it was first invented by Condorcet like 200 years ago, right? The idea there is that we kind of use a probability model. So we assume there exists an ground truth ranking over these alternatives. And every voter's preferences are noisy perception of this ground truth ranking. And then we can build up a noisy model, and then we can use the maximum likelihood approach to convert this profile, observed profile, to find the winner. So basically, these are I would say these are the mainly two approaches I know in social choice, how people evaluate a voting rule. And actually, in this work, our new method is another kind of maximum likelihood model. So I think it's more constructive.
assume that if you vote concurrently instead of sequentially, then the paradox is not, it's not, probably is not a strong vote. I guess you can get much better guarantees.
You mean in this situation?
If the voters do not, if it's not a stackable great game, that you vote sequentially, but if you vote concurrently,
then you're going to end up with very bizarre Nash equilibrium, as I showed in the very beginning. Everybody prefer A to B, but you have a Nash equilibrium where everybody voted for B preferred to A. So you still have a very bad situation.
Depends on the rule.
Oh, whatever the rule is. This is always a Nash equilibrium because no single voter can change the outcome. So if you are thinking about a voting game, then in a simultaneous voting game, clearly you have very bizarre, very bad outcomes. But for stackable voting games, sometimes you have very bizarre outcome, but on average, probably this, what we call bizarre outcome, is actually more preferable. This is left for future research. We want to find theoretical result, but now we just prove it by simulations. So hopefully that answers the question.
So there is some work by Kalai and Mossel on the probabilities for various voting rules to produce paradoxical outcomes.
To produce what?
Paradoxical outcomes. So for things, variance of arrows, paradox, but what are the probabilities?
Oh yeah, I know that. Yeah, they have developed quantitative version of arrows impossibility theorem and quantitative version of Gilbert-Satterwhite theorem. Actually, we have some follow-up work to the quantitative version of Gilbert-Satterwhite theorem. So I would say their results are still kind of negative results. So, so they showed that, for example, in terms of Gilbert-Satterwhite, they show that if you draw and manipulator uniformly random, you draw and a vote for the manipulator uniformly random, then with a non-negligible probability, you're gonna end up with a manipulation, which is a very negative result, right? So it says that not only saying that there exists a manipulation, but it says that manipulations can be found quite often. So I think their results belongs to kind of the first line of results of using the axiomatic approach to voting rule, but they just obtain some negative results. So what we are more looking forward to is more constructive result, we hope.
But one other view of it is it gives you criterion to compare different voting rules in terms of how bad this probability actually is.
I'm sorry, what's the question?
It gives you potentially a method to compare different voting rules by computing this probability for different rules and trying to minimize the manipulation probability.
Yeah, that's true. Yeah, that's true. That should be interesting. Yeah, I'm not aware of any other work in this line of research. That could be interesting. And
if it's always close to one, then
yeah, and another thing.
It's not close.
Another thing people are trying to argue is that in all of the work by Kalai and some other guys, one of the criticism is that they are working on the votes are drawn IID from some distribution. But actually, this is very criticized by economists. They don't like this IID assumption. They would say, okay, in real life elections, often your vote is correlated with other guys, so what would you do? So, so in that line of research, there are some of researchers like Toby Walsh have run some simulations on this result, but so far we still don't get any theoretical result. How can we argue the correlation? How can we quantify the correlation or whatever? And how can we testify these observations? So I think that's an interesting question. Yeah.
So intuition would suggest that in these sequential voting models, the voters who vote near the end have more power. So is that true, or is that...
Shouldn't be any full information on it.
That's definitely a very brilliant question. So you could argue that people in the end have more power, but you could also argue that people in the beginning have more power because that's kind of giving you some information, shedding some signal. And actually in our result,
and your
it is still
example is the one in the middle that had the...
Yes, exactly. Good memory. So it's exactly the ones in the middle who have decisive power. right? Because they rank C1 in the top position, but the other guys rank C1 in the bottom positions. So it's not quite clear.
But if there's full information, doesn't everybody have effectively equal power?
No, definitely not. Because their order definitely matters.
It depends how you define. I mean, power.
Yeah. So the first question is power is not quite well defined.
I'm just wondering if there are any results that sort of give some kind of answer to this question. Because, I mean, here it's just, here is one counterexample. So
Yes,
it doesn't really
yes.
say that the middle people have more power.
Right.
I'm just wondering if there is any result you can point to that
Yeah, maybe we can
answers
just
this question.
yes, maybe run some simulation and see which position has maybe more power over the outcomes, and that's definitely a good question.
In the position somewhere where the balance of power tips can be calculated?
Balance of power tips.
Who has control?
Well, yeah, it's again, it's hard to analyze from a theoretical point of view. Maybe you can run simulations like you pick up a position and you pick up random votes and you see whether or not this random vote will make the winner change or has no power over the outcome or something like that. You could possibly run simulations like that.
So
That's doable.
you could presumably smooth that by giving every voter 10 votes, say, and they have a random different position each time, and eventually take the limit of 1 million votes.
Oh, no way. I mean, now even 20 voters is it's hard. It's very hard to compute the winner. So,
You can imagine, right?
millions.